parametric right-hand sides. All right, so suppose we have a linear program, and the right-hand side vector b is parameterized. You've got a vector b, another vector b prime, and then lambda is your parameter. As lambda varies in the non-negative real interval, you want to know how the solution is getting affected. Let's look at the standard form problem. This is the standard form problem, except that now we have the right-hand side being parameterized. And I'm going to define again the optimum value of this by z lambda. So z as a function of lambda is the optimal cost of this linear programming problem. Let's just assume that the feasible set is non-empty. So for lambda greater than or equal to 0. If it becomes empty for some lambda, you can discover that eventually. So I'm not going to bother with that, but that could be a good exam question, of course. And we'll also assume that z as a function of lambda is finite. So I assume that the problem does not become unbounded. Again, if it becomes unbounded, you can discover that as you analyze the problem. All right, so the first observation we will have here is the following. If you look at the dual problem, this is your dual problem. So the right-hand side parameterization becomes an objective function parameterization. And of course, due to the strong duality theorem, when you have an optimal cost for the primal problem, the same is obtained here when you solve the dual for the same lambda. Okay? So for that reason, if I define my W to be the set of W that are feasible to the dual, then this has extreme points, say W1 up to whatever, say W. Let's make this different, WT, okay? And z of lambda, under the assumption that it's well-defined or finite, it will get realized at one of the extreme points due to the fundamental theorem of linear program, which says that whenever there's an optimal solution, there's an extreme point optimal solution. So z of lambda is the minimum of the extreme point values here for fixed lambda. Wi, which is the ith extreme point, evaluated by the objective function, and you just enumerate over the extreme points, and you extract the optimal value for fixed lambda. Maximum, yes. Mm-hmm. For fixed lambda. Okay, so, and of course, when you look at this thing, this is WIB plus WIB prime lambda. Wi is just a constant. Again, let's just refer to it by alpha. And the other one is another constant. Let's just call it beta I. So you just have a simple linear function, some constant plus another constant times lambda. And if you plot this, of course, each linear function will look something like this. Okay. With appropriate slopes. And for fixed lambda, you're looking at the pointwise maximum of each of these numbers. So you generate this piecewise linear curve, which is the pointwise maximum of all these numbers. So that's your z. It is a piecewise linear convex function. That's because the original problem is a minimization. Okay? If it were a maximization, of course, this would flip around and it would become a piecewise linear concave function. Okay? So, all right, so this is the general character. And the next question is how to compute this. The question is meaningful because the way we characterize this is by assuming that, or you pretend that you know all the extreme points so that you can plot all these functions. Of course, in reality, that's a very expensive computational way of handling things because you do not really want to enumerate all possible extreme points. So, to do that, let's just assume that B be an optimal basis corresponding to lambda equals 0. So first you generate at the lambda equals 0 point, you generate this first extreme point optimal cost, and we assume that's defined by some basis B. And the current solution is, of course, it's xb. And if I take it as a function of lambda, it will be B inverse times B plus B prime lambda, which gives you B inverse B plus lambda B inverse B prime. Let's just give a name to this, B bar, and say B bar prime. So this gives you B bar plus lambda B bar prime. That's your solution as lambda is allowed to become positive. Of course, not for too large lambda because things will switch, but as long as B retains its optimality, okay? This will be the solution. All right. The optimal value is going to be CB times B inverse B, and that will give you CB times B bar plus lambda times CB B bar prime. That's your optimal objective value, which is the value you get here. Okay? At lambda equals 0. Of course, when lambda is different, it starts going downhill or uphill, whatever the linear piece is, whatever the slope is. Okay? The slope is CB B prime, B bar prime. All right. What is the reduced cost vector? The reduced costs are defined by CB B inverse A minus C. That's your W. And of course, this is not affected by lambda. Okay? So all you have to do is the dual feasibility condition is defined by the reduced cost. That's always retained. It's satisfied. It doesn't get affected by lambda. But the other parts, they do depend on the lambda, especially this one, xb. So you have to take care of that. As lambda is increased, we want to retain feasibility of this solution Now this solution at lambda equals 0 is non-negative. Of course, it satisfies AX equals B, that's for sure. But non-negativity at lambda equals 0, well, it is satisfied because we know B is an optimal basis. But when lambda starts increasing, of course, things may lose non-negativity, some of the components. Okay, so we require this solution vector to remain non-negative. That's what we want. Now, if, for feasibility, of course, for feasibility of the current basis, if the B bar prime happens to be non-negative, then, of course, B is an optimal basis for all lambda greater than or equal to 0. So it goes, or it maintains its optimality and feasibility, the current basis, until lambda becomes very large at infinity. If not, then we want to impose component by component. This is the ith component of the vector under consideration. We want to impose this condition. Well, if Bi is non-negative, Bi bar is already non-negative. So if Bi bar prime is also non-negative, this will be always non-negative. However, you want this imposed for all those i's for which Bi bar is less than 0. So whenever Bi bar prime is less than 0, you may eventually make this negative by choosing lambda sufficiently large. Okay? Okay. So all you have to do is we compute, say, lambda 1, which is the first breakpoint here. If you just refer to it as lambda 1. Lambda 1 is equal to minus Bi bar divided by, that's Bi bar divided by Bi bar prime. You want to compute the minimum such ratio from out of those I for which Bi bar prime is less than 0. B is optimal for all lambda in the interval 0 to lambda 1. That's it. That's the first piece in the picture. At lambda equals the first value plus some epsilon, B is no longer an optimal basis because somebody loses feasibility. So, some particular basic variable which supplies the minimum ratio in the computation of lambda 1, becomes negative. Why? Because at that point, xbr as a function of lambda is going to become, well, where do we have it? We have it here, br bar plus lambda 1 plus epsilon. This is the value of that particular variable. And of course, this will give you br bar plus lambda 1 times. Lambda 1 is how much? Minus br over b bar prime r times br prime plus epsilon times br prime. Now this part is of course 0. Things cancel. And this part is negative because br by assumption is negative. So epsilon times that will be negative. So that will be a negative component. Okay? For that reason, all you have to do is we just look at the tableau here. This is the rth row of the tableau. In other words, you have the tableau for lambda equals 0. And then on the same tableau, you can simply change the right-hand side as being dependent on lambda. And for lambda equals lambda 1, you can recompute the right-hand side. And for a little bit larger than lambda 1, in other words, when you add epsilon to it, this is the right-hand side for that particular variable. So this guy is negative now, so it should go out. And then you look at your numbers here in that row. You inspect or you find the negative ones, and then you look at the appropriate ratios of the top values to those, and then you enter a qualifying variable. Using the dual simplex criteria. Then you compute your new optimum basis. It doesn't have to be in the immediately next iteration. It may take maybe more than one iteration. Why? Again, no answers. That's okay. Why? Anybody? Are you guys following or just writing? I'm sure you're following, but nevertheless, you know, when the question comes, you don't give me any answers. All right, it's very simple. If you have a unique ratio, a unique index that gives you the minimum ratio, in that case, of course, you've got only one negative number here. So when you remove that, you will normally get non-negative on the right-hand side column, and you'll be fine. Okay? In other words, you'll get the optimum point, optimal basis immediately. However, if you have more than one index, many indices giving you the same ratio, the same minimum ratio that supplies the value of lambda 1. In that case, of course, you've got many negatives here at the same lambda. And of course, it may take a number of iterations to get rid of all of them, okay? For that reason. All right, but this is basically the idea. So if you don't have any questions, now I'm going to switch to a new topic, which is decomposition for linear programming problems. This is a new chapter in your book. Not in your life, but in your book. Okay, so decomposition. Now, I know at least 2 people are familiar with this in the class because I covered decomposition to some extent in the undergraduate optional course, the elective course. But other than the 2 of you, anybody familiar? Maybe from where? LU decomposition has nothing to do with this. Okay. Yes, okay, sorry. Yes, the 3 of you. Anyone else? That's it. Okay. So for the people who know about this already, this may be a repetition a little bit. Nevertheless, for the newcomers, we'll just have to go through this. All right, what is the main idea? First of all, decomposition is quite handy, and it's I think a very creative, an innovative way of looking at such problems. Suppose you have some kind of a linear program, and if you ignore certain constraints, then the linear program under consideration has a special structure. Special structure meaning that it's easy to solve if you had not had certain constraints additionally. Okay? So ignoring those constraints would allow you to solve the linear program quite easily. But life is such that you do have those constraints. So what you do is you want to take those constraints and treat them on the side so that the problem actually decomposes into a part which is easy to solve, but then the part you extracted out of the problem, you have to deal with it on the side. So you have to know how to do that, which is not easy. So that's the main idea here. So let's suppose the problem under consideration is the standard form problem. Except that I'm going to write a set constraint here, which collects all of the constraints that I want to deal with on the sides. Okay? So this is just a polyhedral set of some sort. It's this, it's the part of the problem which makes the problem more difficult than it ought to be. An example of this is the following case. Suppose you've got an A matrix. This is the left-hand side. I'm not referring to this, but I'm referring to the entire problem structure here. In the A matrix, you've got non-zero numbers, coefficients on the left-hand side. So you've got the constraints here, say, in whatever form. Okay, this is the right-hand side vector. In the lower part, you've got the so-called block diagonal structure. You've got a matrix here, another matrix here, and another matrix here. So you've got small submatrices along the diagonal. But the rest are all 0. Okay? Everything else is 0. Now, if you had ignored, for example, these constraints, this lower portion of the problem would decompose into the block diagonal subproblems. Okay? So that would be easy to handle. However, these coupling constraints, these constraints actually are the ones that allow you not to decompose the entire problem. So these constraints they make the problem more difficult than it is supposed to be. So that's one example of that. So what we're going to do is we're going to, let me assume X is bounded. So let's handle the problem under that assumption first. Okay? When you have a bounded polyhedron, this is your X. But the feasible set does not consist of only those points, but then you've got the additional constraints which tells you you are supposed to have this. So the additional constraints, for example, if you have a single equality constraint, you would have that. It will give you a lower dimensional polyhedral set. Okay? And your feasible set is actually this part. If these are the constraints that satisfy AX equals B. So your actual feasible set is this. However, if you ignore that part, it looks like that. Okay? So what we're going to do is we're going to pretend that we know the extreme points of X. These are the extreme points. And then you know that you can express any point inside X as a convex combination of the extreme points. So when you assume you know the extreme points, they become known vectors. Okay? But now, what are the multiplies, the lambdas or whatever that you use in the convex combination? You don't know. So they become your new variables. How many new variables are you going to have? Well, as many as you have extreme points in the X set, which could be very many, actually, too many, usually. Okay? Nevertheless, you pretend that. Once you do that, you can actually start working with a very small subset of the extreme points. That's the idea, but you need to know the mechanics of the simplex method for that. The main idea being that we work with a basis matrix rather than the entire set, and the basis matrix allows you to work with only as many extreme points as you would have columns in the basis. That's the main idea. How do we do this? Let's just see what we can do about that. So let, for example, x1 up to whatever, xt be the set of extreme points of X. And then for any point X in the polyhedral set large X, we have multipliers lambda 1 up to lambda t such that X is equal to lambda j times xj, j going from 1 to t, with lambda j's being non-negative for every j going from 1 to t. Additionally, of course, we must require lambdas to add up to 1. Okay? So, now we can substitute for this. In the original problem. So we want to minimize Cx, which now becomes C times lambda j xj, subject to Ax equals b becomes A times summation lambda j xj equals b. And x in x is no longer needed because you already expressed x as a convex combination of the extreme points of capital X. We additionally require lambda j equals 1, adding up to 1. And lambdas are non-negative numbers. Okay? All right. So if the initial problem had m constraints here, we ended up with m plus 1 constraints here. And your variables are lambdas now rather than anything else. Okay? Of course, this requires some simplification. when you simplify, what do you get here? You get summation C times xj lambda j. That's the cost coefficient associated with lambda j. I'm just taking that. This is simply the objective function relative to the cost vector C evaluated at the jth extreme point of capital X. Okay? Subject to, let's also simplify this guy. What will it be? It will be summation lambda j times a xj. Let me just write it this way. J going from 1 to t equals b. And then you also have, of course, this is like that, okay? A times xj, it just gives you a column vector. And that's what it is. And then you have summation lambda j equals 1. This is a single constraint with lambda j's being non-negative. Let's define Cj cap to be C times xj, the cost obtained at the jth extreme point of x. And let's define aj cap to be A times xj. That's just a column vector. That's what we have. Okay, so with that, I can rewrite the whole problem in a little bit more comprehensible way. So the problem becomes minimization of Cj cap lambda j subject to summation aj cap with a 1 times lambda j equals b and 1. So I just took the column vector axj, which is now aj cap. There's a 1 here for the jth variable. So that column plus 1, that becomes a, it's just the column associated with lambda j. That's what I did here. And you're just adding up these things. On the right side, you've got the vector b, but for the last component they should add up to 1. Okay? So, plus lambda as a vector or as variables they are non-negative. Okay. How many constraints do I have here? I have m plus 1 constraints. Whereas in the original problem, we had m constraints for ax equals b part, plus possibly many, many more constraints in the capital X portion of the problem. So we got rid of all those capital X portion of the problem. But what is the trade-off, or what did we... so we actually gained something in the number of constraints, but we lost something in the number of variables. There are too many variables here. There are too many lambdas. How many? As many as there are extreme points of the ignored set, or capital X. Okay? All right. So if you worked with a regular simplex method using a basis, what size basis do you need? You need m plus 1 by m plus 1 basis. Which means that if you know, for example, some n+1 initial basic variables, lambdas, which correspond to, of course, n+1 extreme points of capital X, you have at least a beginning. You have a basic solution coming from the appropriate extreme points of the capital X. And then the next question is, well, fine, we do have a solution to start with, but now what do I, or how do I improve the solution? So you need to go through the regular mechanisms of simplex method, compute the reduced costs, etc., and then find a qualifying entering variable, which will correspond to a new lambda, which corresponds to another extreme point of X. Okay? So the main question here is, once you know what to enter, then it's easy to compute which one to exit. Okay? But the main question is, how do I compute the reduced cost? Because I've got so many zillions of variables here, if you decide to compute each one at a time, it's just too expensive. All right. So suppose we have a feasible basis on hand. Let's assume it's B. Okay? And B is, of course, n+1 by n+1. Okay? That's the size of your basis. Think of the revised simplex tableau. Now, in the revised simplex tableau, we put the basis here, or the basis inverse actually, right? So suppose you've got your basis inverse here. What am I supposed to have here? You have B inverse times the right side. So that's going to be, I must have given a name to it. I don't want to deviate from my old notation because it creates problems later. I called it B bar. So this is B bar. The way you compute that is B inverse times B and 1. Okay? That's your B bar. Okay. We have Z bar here, which is CB cap times B bar. Over here, we have the dual simplex multipliers. Now, I'm going to use Wn alpha for that, where Wn alpha is just the last component of, this is an n plus 1 by n+1 vector. 1 by n+1. Okay? That's the dual simplex multipliers. The W portion is 1 by m. Alpha is the last component. Because we have a special, that's the, it just comes in easy this way. All right, so what is the definition of this? W alpha is simply CB times B inverse. Of course, CB cap, we're using the cap data. Okay? Okay. Computing the reduced costs. That's what you need to identify an entering variable. Now, your reduced cost is Rj, and by definition, it's CB or W alpha, which is the dual simplex multipliers, times the column associated with lambda j, which is Aj cap and 1, minus Cj cap. This is the reduced cost associated with the variable lambda j. We're working with this problem. This is the master problem. Maybe we should give a name to it. Master problem. which is your working problem. Okay? All right, this is the reduced cost associated with lambda j, variable lambda j. Of course, for basic lambda, these are 0. For non-basic lambda, we have to somehow generate them. Okay? And so this is going to be W times AJ cap plus alpha minus CJ cap. And since this is a minimization problem, we want the maximum or the most positive one. So you want to compute the maximum reduced cost, which is WAJ cap plus alpha minus CJ cap, J going from 1 to T. That's what you want, if you're able to do so. But this computation is computationally very expensive. Because you've got too many extreme points. So you need a more intelligent way of computing this. If you're able to compute it without spending too much computational effort, you're essentially done. Then it will tell you which variable to enter, and then after that it's a piece of cake. You know, it's easy to handle the rest of the problem. All right. So here, there's a cap here. Don't forget your cap. Okay. You just observe that the maximum of these things is the same as W times AXJ. I'm just replacing AJ cap by its original definition, plus alpha, which is, what is alpha here? Well, it's alpha, minus CJ cap. What is CJ cap? C times XJ. This is what we're looking at. Now, this is the same thing as maximizing over J of W A minus C times XJ. We're just factoring out XJ here. There's also another constant alpha here. Alpha is a known number. Okay, so this alpha, of course, does not affect the maximum here. So you can take it out. So alpha plus maximum of WA minus C times XJ. Now, here's the catch, or here's the important critical observation. XJ, when with alpha taken out, XJ is just the jth extreme point of capital X. So instead of enumerating, what you're doing is you're looking at the jth extreme point here, you're multiplying that with a cost vector. What is your cost vector? It's WA minus C. It may change as dependent on W. Other than that, of course, things will not change, in other words. But this is a computable thing, and you've got it on hand because W is already available from the current basis. Now, with that, this is just the cost vector times extreme point, which means you're simply trying to solve a linear program with unknown x here, which will give you an extreme point of the set capital X. That's what it is. And I think once you observe that, things become very easy. See, all you have to do is you need to solve a linear program here. And then once you solve this linear program, what linear program is that? It's the linear program whose cost vector is WA minus C, and whose feasible set is defined by capital X, which is the ignored portion of the initial problem. All right. So this gives you a value. So let X bar solve the problem, maximize WA minus C, X, X in X. Of course, there's an alpha here, which is supposed to be added to the objective value once you solve it. So don't forget that, okay? We call this the subproblem defined by the dual multipliers W and alpha, because W is here and alpha should be added to the objective value. This is the optimal solution. And then compute, say, R bar, which is your maximum reduced cost, which is going to be your alpha plus the value you would get from the optimum solution. Okay? That's the maximum reduced cost. Clearly, this value is greater than or equal to 0. To me, it's clear. I'm not sure if it's clear to you. Why is it clear? Huh? Say that again? Because of alpha. Not really, no. No. The reason is the following. The reduced costs refer to the reduced costs of the non-basic lambdas as well as basic lambdas. The basic lambdas already have reduced costs of 0 by definition. So you're looking for the maximum reduced cost, but you already know that you have reduced costs of value 0, so the maximum should be greater than or equal to 0. Okay, that's for that reason. All right, if the maximum reduced cost you get happens to be actually equal to 0, then nothing else can come in anymore, so you are optimal. Then B is an optimal basis, so the corresponding solution defined by that particular B is optimal. If not, then you have a positive reduced cost, then enter a variable. So let's just call it, say, lambda bar, corresponding to the extreme point x bar of capital X. Because you already generated a solution here, which is an extreme point of X. And that particular extreme point has a certain lambda variable, which we don't know yet, but it will become basic now. So enter lambda bar. Oh, I already said that. Enter a variable, say, lambda bar, corresponding to that extreme point. So in that case, you go back to your revised simplex tableau. This is the tableau you had. So you identified a variable lambda bar. I just called it lambda bar, which has a reduced cost of R bar here, which includes alpha. Okay. And what do you need here? You need a vector y bar, where y bar is, what is it? It's the current inverse times the column associated with that. What is the column associated with lambda bar? A times x bar with a 1. That's the column. Okay? Looks kind of complicated, but it's really not. I mean, if you just follow the stream of thought here, I think it's a very innovative way of handling. So anyway, this is what you have. Once you enter this, you look at your regular ratio test, and then you know how to proceed after that point. Now you deserve a 10-minute break with this, I think. I'll give you other additional details later, next Monday, on Monday. Okay?